In this video, I'm going to talk about how to approach an integration problem that involves a product of sine and cosine with different angles. As an example, you see here I have the integral of sine 4x times cosine 7x dx. Now you cannot use u substitution on this integration problem. U substitution will not work. Although that is a good first thought, because we know we could allow u to equal sine and the derivative would be cosine, but those angles must match in order for that substitution to work. So if we tried to let u equal sine 4x, du would be cosine 4x and then times 4 because of the chain rule, dx. And cosine 4x is not what we have in the problem. So what we're going to do instead, product to sum formulas are not as common for people to have memorized as the sum and difference formulas. And the product to sum formulas can be created using the sum and difference formulas. So I'm going to show you how I just use the sum and difference formulas to figure out how to rewrite this integrand as either a addition or a subtraction between those trig functions, which therefore would allow us to integrate them separately. I like the sum and difference formulas better also because I've got a little story I have created in my head to go along with how to remember them, which is always helpful. Anytime you can attach any additional stimulating knowledge to something you're trying to memorize, it's just extra things I feel like it's associated with in your brain and more possible connections of finding it. So the sum and difference formulas have to do with how to break up an angle where there is a sum or a difference inside the angle. And I'm going to start with sine, but then I'm also going to show you for cosine as well. So I'm going to start the story as I write out the formula. So I like to think of sine as the nice guy. Sine backwards is almost nice. So sine is the nice guy. And what that means is when he breaks apart a sum or difference inside of his angle, he's going to share with cosine. So sine is going to take on one of the angles, and he's going to share and let cosine take on the other value. The other nice thing about sine is that whatever operation you see there, you will have the same operation in between the two terms in this identity. So remember, sine is the nice guy. He likes to share, and he keeps the sign exactly the same. He's not going to change that on you. And for the second term in this identity, they're going to trade. So sine is going to take on the y value. Cosine is going to take on the x value. So unlike sine, cosine is the mean guy. Cosine is selfish and tricky. He's selfish because he does not share those angles with sine. He does not want to intermix or mingle with sine. He wants to take on both of those values first and by himself. So we've got cosine x, cosine y. What makes him mean is that he's going to switch the sign on you. So if you had addition here between the angles, it's going to turn into subtraction. And I used the same color and I put it on top to show you that they go together. And if you had subtraction here in this angle, he's going to change it to addition. So he always changes that sign on you. And then he will allow sine to take on both of the values. So in both of these formulas, we see that the angles do eventually get applied to sines and cosines, but how those factors and those terms are combined are slightly different between these two identities. So you can't just distribute a trig function into its angle, because distribution is an algebraic operation, and sine is not an algebraic function, it's a trigonometric function. So in order to break up an addition or a subtraction inside that angle, we have to use this identity to get it expanded out. We look at this side, the right-hand side of those identities, and try to identify which piece we're dealing with. Do we have a mix of sines and cosines? Do we have strictly cosines, or do we have strictly sines? Those are the different things that we could possibly see. So here we have a mixture. If we have a mixture, that means we're going to be separating out into a sum or difference inside the angle of a sine. If we don't see a mixture, if we see only cosines or only sines, then we're going to be switching it out for a sum or difference inside the angle of a cosine. Because remember, cosines mean, so he wants to take on those values all by himself, and then later he'll let sine take on the values by themselves. So you want to start by identifying which of those pieces you need. And in our integral, we have a mixture of sines and cosines. So remember, when there is a mixture of sines and cosines, we must have been using that sine identity. It really doesn't matter which one of those we consider to be the x and the y, but that's exactly what we're using these for. The x and the y here just mean two different angles. So this could be 4x, this could be 7x. So I want to try to figure out a way to isolate this guy while also figuring out a way to replace this guy. So I'm going to take that one formula and move it down so we can manipulate it. And I'm going to pull down the plus or minus that we see in there as well. As I pull that identity down, though, I'm going to separate it out into its two separate plus and minus options. So we could have sine of x plus y, and that would separate out into sine x cosine y plus cosine x sine y. The other option is that we have subtraction in there. These two terms are going to stay exactly the same. The only difference is the operation between them changes to subtraction. So we're going to think of this as a system of equations where we want to only keep these guys, and we want to get rid of somehow these guys. Well, one way we do that when we solve systems of equation is by elimination. And to solve by elimination, the pieces that we want to cancel must have exact opposite coefficients, which these guys already do. So what we're going to do is we're just going to add down on this equation. We're going to get sine x plus y plus sine x minus y equals, now these two match, so we have two of them. And these two also match, but they have exact opposite coefficients, which means they cancel out. And remember, this is what our integral looks like here. It doesn't necessarily have that 2, so we need to divide it over. So this tells me I can replace sine x cosine y with 1/2 of the sine of x plus y plus 1/2 the sine of x minus y. So I distributed the half to both terms, but since we're doing integration as our next step, you could also pull the half out in front. So let's remind ourselves why exactly we were doing this. We were asked to integrate sine of 4x cosine of 7x. And we just found a way to separate that out into 2 pieces, 2 terms. And when we have it separated into terms rather than factors, terms can be integrated individually. So sine 4x times cosine 7x, these are the angles we're working with. And these are what we're going to be plugging in for the x and the y in that formula. So it's 1/2 the integral of sine of the 2 angles added together, so sine 11x, plus sine of the difference between the 2 angles, which would be 4x minus 7x is negative 3x. You can now work these 2 integrations individually with a u substitution for the angle. There is one other identity, though, that would be helpful here, and that is to remember that sine of a negative angle is equivalent to negative sine of the positive angle. So this isn't what we're actually doing, but this is how you can remember it. When it's a sine, a negative inside the angle can be factored out. When it's a cosine, it cannot. And this is actually an identity. So sine of a negative angle is equal to the negative sine of the opposite. If you get it inside of a cosine, though, cosine is an even function, and what that means is the negative and positive inputs have the same values. So a negative inside of a cosine really just cancels out. A negative inside of the sine factors out. So now that would make it a little bit easier, and we could do a u substitution here for 3x and get that antiderivative. And don't forget, at the very end, the 1/2 applies to the whole thing. I encourage you to pause and try to finish this one, but I am going to write the answer below. If you want to work it, pause now. So for the antiderivative, I got negative 1/22 cosine of 11x plus 1/6 cosine of 3x plus c. This is obviously only one way to approach these problems. I'm sure there's many, many, many other ways to do it. I do it this way specifically because when I teach trigonometry, I teach my class to remember as few of these as they absolutely have to, as few of these identities, and then I teach them to create the rest of them. You just have to know how to create the rest of them, what to look for. So this way I just showed you is how to create the product to some formulas. If we're asked to integrate cosine 9x cosine 3x dx, anytime I see a product with 2 different angles in the trig functions, we know we're going to have to use those sum and difference formulas. So I'm going to write them out. And I'm remembering already that sine involves a mixture of sine and cosine, and that's what That's not what we have here. We have strictly cosines. So I know it's going to be the other formula. So that saves a little bit of time. I'm thinking ahead. Cosine of x plus y. Remember, cosine is the selfish guy. Cosine x, cosine y. He's also the mean guy. He's going to change the operation on you. And we need to write both of them because remember, we think of this as a system of equations that we're going to use to isolate the piece that we want. So if we change that to subtraction, the terms stay exactly the same. That operation is what changes. So what we're looking for here is two cosine functions with different angles, which are right here. So I want to use elimination to add these two equations together and get this other product to cancel. And if you look in front of those second terms, their coefficients are already exactly opposite. In top we have a -1, and the bottom we have a +1, which tells me I can go ahead and add these together now, and those pieces will cancel because I have -1 of them and +1 of them. So what we get is that cosine of x plus y plus cosine of x minus y is equal to 2 cosine x cosine y. And we want to solve for cosine x cosine y. So I'm going to divide that 2 over as a 1/2. And I'm just going to keep it out because I'm going to then pull it to the front of my integral. So any product of the cosine of two different angles can be separated out using this formula. We have the angles 9x and 3x, so that's what we're going to be plugging in for these two here. 9x and 3x. 9x and 3x. So instead of the integral of cosine 9x cosine 3x dx, this formula here says we can replace it with that. So 1/2 of the integral of cosine, and those are like terms, so we can go ahead and add them together. That's cosine of 12x plus, and 9x minus 3x is 6x, cosine of 6x. So what we have succeeded in doing is turning that product into a sum. We can't just integrate them one factor at a time. However, we can integrate one term at a time. So the trick for this one is to use those sum and difference formulas to figure out how to separate that product into a sum. And now each of these can be calculated individually with their own separate u substitution. So we're going to get 1/12 sine of 12x plus 1/6 sine of 6x, all times a half. So if you want to, you can distribute. You get 1/24 sine of 12x plus 1/12 sine of 6x plus c.